So, welcome everyone to this session in the Efficiently Deploying NSO live session track. My name is Magnus. With me I have Rocky. We will be answering questions that you pose in the Q&A section of the Cisco WebEx events application. The session is about using NSO in Docker for CI testing and development. It's presented by Kristian Larsson, a many-year user of NSO, who is now part of the NSO CTO team. Take it away, Kristian.
All right, thank you, Magnus. Okay, so in this session, I will take you on a journey towards a better development environment for Cisco NSO. We're going to talk about NSO in Docker. As always, I have slightly too much content to squeeze into a slot like this, so expect a rather high-paced session. But I hope you had your morning coffee and can follow along. Let's dig in. So I would first like to focus on the question of why Docker? Why is it that Docker is so popular and what's the key to its success? In answering this, most will focus on its technical properties, like how containers are more lightweight than virtual machines or how they provide a higher degree of isolation than regular Unix processes. I think it's mostly about ergonomics. Docker provides for great ergonomics for developers. Developers need to write code and any other task like starting test environments for reproducing problems or testing with all the moving parts that comprise a complete system is ultimately a time sink. It takes away from the time that you could be spending on writing code. And so the less time you spend on these sort of peripheral tasks, the better. Docker helps in this area by taking a lot of common procedures and making them really quite simple. So it's getting stuff out of your way. Similarly, we want to remove all the friction and pain associated with deploying and getting NSO up and running in various environments to allow for development, testing, and ultimately production. What NSO in Docker offers is a form of codified best practice and way of working that will help you with these peripheral tasks so you and your team can focus on what's important. Ergonomics and the developer experience is truly front and center in this, but there are a few more things that we want to achieve, and I want to start by just outlining them here. So what we're trying to accomplish first and foremost is the sort of best practice for a way of working. And it's not just a paper product, there's code to go along with this, so you can hit the ground running. Overall in the Docker world, or NSO in Docker world, we want to encourage composition of things. So we want to be able to build small components that can be tested in isolation and then be brought together to form a larger whole. And I'll show you what I mean by this as we go along. A likely consequence of that is that you'll end up with quite a few Git repositories to manage. And so for this, we have the concept of a standard form, which repositories are encouraged to adhere to. There are currently 3 different skeletons for 3 use cases, and those are for NEDs, for generic packages, and for composing an entire NSO system. All the skeletons have a standardized and uniform interface, which I'll also show you. So we're going to talk about a shareable work environment for development and testing. So this is a really important concept, which we'll also cover. And last but certainly not least, something we call one-click CI, which you can probably guess what that's about. Now, I want to talk about this common way of working, but in order to do so, we first have to understand how we interact with the typical Git repository that contains some NSO project. So I think there are 3 main parts to it. We edit files, we compile or build our project, and then we run and test it in order to validate our code. Now, editing files is mostly out of scope for the repository skeletons. There are plenty of good text editors out there, so we just don't need to do much in this area. For the build, the standard form skeletons have you covered and offer a simple make target called build in order to compile and build your project. Similarly, for testing, there is a standard target called test that will spawn a test environment and then run the test suite. And this is what makes up part of this standardized interface that I've been talking about. And I'll show you this in practice in a second, but just before, let's talk a little bit more about testing. So testing is a natural part of development, and it's usually one of the most difficult areas, actually. And doing development with NSO, I think, poses further challenges. NSO is a system to manage devices, and so in order to test it, we can't just run NSO standalone. We need devices around NSO that NSO can talk to and interact with. So our code is about this interaction with the devices, and so we need them in order to verify our code in NSO. We can think of this as our test environment. And to build such an environment, some will scream NetSim, others will talk about virtual routers, or heck, maybe even using physical devices. Regardless of which you choose, I think one of the most important aspects is that we codify this environment. So let's say we're a group of developers, we're a team. Now we have to be able to code against the same test environment. If you use virtual routers when developing some NSO service, then I have to be able to use the same kind of setup, the same test environment as you, or development will be really hard. I will more or less be struggling just setting things up just the way you've done it in order to be able to do that development. So the idea here is that if we write down in code what constitutes a particular environment, then someone else can reuse that same environment, or even better, they can get their own instance of it, at least if we're talking about NetSims or virtual routers that you can just spin up and instantiate, right? So we do this with the NSO skeletons by introducing the concept of a test environment, which we call simply testend. And that's a shareable work environment that has a standardized interface. So with the test environment codified, it's easy for John here on the right to have his environment, while our younger engineer, Tim, here on the left, also gets his own. Also, apparently, I guess development is supposed to happen on an iPad these days. Okay, so enough slides. It's demo time. I'm going to switch over to a terminal, and I hope you can see my terminal. Not someone will need to scream. So we're in this directory called Cisco IOS CLI 644, and this repository contains the Cisco IOS CLI NED placed in a Git repository that uses the NSO in Docker repository skeleton for NEDs. That's a bit of a mouthful, but so it's using the standard form that I've been talking to. It adheres to that, right? And now to build this repository, just like I showed, we simply issue make build. Now I already built this package before, so building it again is pretty fast since it's using Docker's built-in cache, and without the cache it would take considerably longer. Next up, we want to test our repository, and there's a target for this. As you saw before, it's called make test. Now I want to break this down a little bit and do it sort of step by step so we can see and understand what's going on. Fortunately, that's easy because make test actually consists of 3 separate targets that are called test and start, test and stop, respectively. And I think you can guess what they're doing. So we're going to start here by just running the test and start. Now, if you imagine, for testing a NED, what do we need, right? First, we need an NSO instance, and the test environment, fortunately, includes one. That NSO instance has the NED loaded, and while most types of errors that can be made when building a NED, like you break the YAG models, these can be detected at compile time, but there are also errors that can only be detected at runtime or load time. So just loading this up in NSO is actually in itself a valuable test. But second, we also get a NetSim container that contains the NetSim compiled version of the NED, and right there, it's done. So we can see here how it started up this environment for us. There are now 2 containers running. The first of which is the NetSim, and then the second of is the NSO container. So with these 2 containers, we can now test the interaction between NSO and our simulated device. As part of the startup that we saw scrolling by here, it doesn't just start these 2 containers, it also adds the NetSim container as a device in NSO. That happens, let's see here, here load merge add device.xml and commits it, right? We see commit complete. So we can take a quick peek at that file. So this is the configuration that it loads up, right? And this is the device definition, the device name dev1. And here's a cool feature. So the address that we use to reach the device, maybe you expected to see an IP address here, right? But it's actually a name. It's also dev1. And this is, going to open up a second file here now on the left that shows you the actual commands used to start up the NetSim container, and this is the actual command. And if we look closely, we'll see there's an argument called network alias dev1. So this container has a network alias that's dev1, and that's why we in this configuration file can use the dev1, which is a sort of DNS name. And Docker will resolve this to the actual IP address of that container for us. This is also started in its own isolated Docker network, so this won't collide with anything else. You can see that here at the very top where it does a Docker network create. So that's really damn useful, if you ask me. You have, I mean, you can write, the test cases become very simple to write since you can use these sort of fixed names in it. Okay, now after this, we want to do the actual testing. So that's the test and test target. I'll start that up. See what it does here. So the test included here is quite a basic test, right? And the point isn't really that everyone should be using this, but this is included in the NED skeleton more as a boilerplate that you can start off with, and it's actually a somewhat useful test just to make sure that some basic properties of the NED and NetSim combination work. So what it does is we start here, we do a sync from on the device. So we read in the configuration that's on the NetSim. That's probably empty, but nonetheless, we read it into NSO, result true here. After that, we configure the host name on the device through NSO, and we do this by loading up the configurations. We load merge /device config hostname.xml. We can take a quick peek at that XML file. So what it does here, we see devices on the dev1 device. You have the configuration, and here we write host name. It's according to the Cisco IOS CLI NED namespace, and we write the host name foobar host name, and this is sort of our magic string here. We quit this. So after we configure that, what we do in NSO is we show the configuration, so show configuration device dev1 config, and we grep for this magic string. So if we find that, we see that as a our success condition that this essentially worked out okay. And just to be extra certain, we then proceed to do another sync from the device. So we actually fetch the configuration to make sure that we get the configuration that's on the device. And again, we grep for the foobar hostname. And this just ensures that we actually were able to write that configuration to the device, and it's there. And again, I mean, when you're writing tests, feel free to do something else. You can use some other test framework like Python unit test. You can use JUnit in Java, Lux, the robot framework to perform the actual test. But regardless of the test framework, you first need an environment to work in, and that's part of what NSO in Docker offers. Now, if we want to play around further in this environment, we can do like this, test and CLI. This gives us a CLI in that running NSO container. You can do show devices brief here or something else. Look at the version of NSO. We can also get we do test and shell. We get a shell inside of the running NSO container. We can look at the processes or log files here. We want to have a look at them. Okay. Whoops. Here's my terminal. There we go. Okay. So if we look at the names of the containers that we have, we see that they end with this NSO and NetSim, right? The part previous to that is common, at least for this test environment. So it actually starts with test end, so we know sort of what it is. Then it includes the project name, which is this part, the NSO version, and KLL here, which is my username. And this is what happens when you start a test environment locally, like I did here. So the username is going to be included in the name of all the containers, which makes them unique. It's quite common, I think, that in particular, if you're using virtual routers, you're going to run this on some big, hefty machine, with a terabyte of RAM or something like that. And maybe you have multiple developers sharing the same machine. So when they want to run multiple test environments, they won't collide with each other because they are made unique through the username. If you instead run this in CI, then it's not going to use the username. Instead, you're going to see the CI pipeline ID. And similarly, the idea behind that is to make it unique so that you can run multiple CI jobs in parallel on the same machines. It also includes the NSO version 5.3 here. And I didn't show you this before, but this is something that you define. So I have this environment variable that's called NSO version, and the value of that is 5.3, which is why the test environment we just started is based on 5.3. That also influenced the make build that I did earlier. So we actually built it for NSO 5.3. And I'm going to show you here, we can do the same thing. So if we just set this, I don't need to export this, I just set it for this single command. We can do the same thing. We're going to do make build, test, and start. You can just rack up commands here to make multiple targets and give it the CLI. And now we're doing that for NSO version 5.2.1 instead of 5.3. So I'm going to start that running here, building everything for us. Now, with this, it becomes very cheap to test against multiple versions of NSO in parallel. So by cheap, I mean all we have to do is change that environment variable, right? It's very simple. And I think this is really useful and really powerful because I think a lot of people sort of suffer from upgrading NSO often enough. Usually, this is associated with some risk, and it's a lot of work sort of doing that upgrade, right? Now, usually, so being able to test your code in parallel, like we're doing here, is really a game changer. Because doing that, you can continuously make sure that it's working across multiple versions. So when you decide to switch NSO version, it's really not that painful. You've already made sure that it actually works on that version of NSO. So here we see it just started up. We can look at, just make sure that this is actually NSO version 5.2.1. Otherwise, this environment looks just the same as the other one. It's just a different version of NSO. And I can show you here, so now we have 4 different containers running, 2 in each of these test environments. And again, they're not colliding because they each have a Docker network that's isolated from each other. So we can use the same name, the dev1 name in both of these to refer to the NetSim device. And again, I didn't actually overwrite my environment. So NSO version here is still set to 5.3. So if I run some other command like this, show LCS state version, you'll see that it actually runs on the 5.3. And again, I can explicitly run it on one of the other ones. Just to make sure I'm not faking this, we can run it on 5.1, and there's no such container running. Typically, you want to test against maybe 2 or 3 different versions of NSO. So you have your current one, let's say that's 5.2.1. Then you want to test against the next maintenance release, so that would be 5.2.2. You also want to test against the next major release, so like 5.3 or 5.3.2 or maybe even 5.4, that's around the corner. And potentially you also want to test against an older version. So let's say we just moved to 5.2.1 from 5.1, then it would be a good idea to also test with 5.1 for some time going forward, just to make sure that all the code we have is actually still working on the older version, because that enables us to go back to the old version if we need to. Okay, so I'm gonna switch here to a different repository that's called BG Worker. So I want to show you a typical development cycle, and there's not enough code sort of in the net there, so I'm picking this other generic package that has some code. So we're gonna run the same thing, make, build, and test and start, which builds again and then starts up the test environment for this package. Now, BG Worker, it's an NSO package, but it's really a Python library that enables you to write background workers for NSO. So it handles some of the aspects that you have to deal with when running an NSO, like redeploys, work correctly, log files, things like this. Together in this repository, we also have a test package that tests the library. So I'm going to show you here. We're going to open up the shell, and we can see. So the test package that uses the BG Worker library, all it does is print these log messages once every second. And it's actually printing 4 different messages on different log levels. So let's say we want to change this. We just want the single log message. So we go in and we edit the code. Let's see here, test BD worker, Python, like that. And so here we have the different ones, right? And let's just keep the warning one. Now you might imagine that doing this, we have to now rebuild everything, right? We have to tear down all those containers that we have running and start the thing up again. And while we've seen that that's pretty fast, it's still not really fast enough for doing, you know, your normal development cycle. You want to edit a file and then you want to load it up immediately. This is thankfully possible due to Target, or thanks to a target called test and build. So we're going to run that here. I'm going to add a time on it as well, just to see how fast it is. So it actually ran Pylint there. Okay, so the total command took 4 seconds to run, and I think a good 3 seconds out of that is probably for Pylint, which is sort of slow. But what it did here now is reload our packages. So we've seen reloaded packages. And now if we go in the shell, we look at that log file again, we see that, yeah, indeed, we now only have the single message being sent. We can run that yet again, test and build, that is. Pylint takes just as long. That should be made idempotent. And this time around, we see it didn't reload our packages. And that's because there were no changes between these 2 invocations, right? So if we go and change again, let's say hello to NSO Dev Days 2020. Now we run a build. Now we're going to see Pylint taking time again, but then it actually does a redeploy. And this is usually how it works, because it's smart in this way. It's able to figure out the most efficient way of loading up the package into NSO. So here, so we only changed Python, and that's why it was able to do a redeploy. Why, you might wonder, why did it do a reload the first time? Well, it actually always does a reload on the first time. So that's just the way. It's difficult to get around that. I'm going to talk more about TestM in a second, but I think this concludes sort of this demo part. And I think this demonstrates the most common operations that you have with the typical Git repository and how the NSO and Docker skeleton helps you out working with that. Okay, let's switch over. So test and build, right? On a very high level, what it does is loads code into running NSO container, or running NSO that happens to be running in a container. So if you imagine our Git repository, and then we have an NSO 521 container, and we have an NSO 532 container. Now, if we want to load the new code into 521, what we do is issue this command, right? So it's make test and build, and we've set the NSO version to 521. This is going to copy the source from the Git repository into the container. It then starts up a helper container that compiles and writes the output into the running NSO container. Similarly, for the 5321, we do make test and build, but specify the 532 NSO version. It does the same thing. It copies the source, starts up a helper container that's also 532, and writes the output into that container. So that means in the Git repository, we keep our source, but we have no binary output. And test and build will, it's actually under the hood. It's using rsync to do that copying of the files, and it's analyzing the files being sent to see what changes have been made. And it's based on that it either does a package reload. So if you change the AI models, for example, you have to do a package reload. If you only change Python code, then it can do a package redeploy. It also takes into account the version of NSO. So in NSO 5.3 and later, if you have made changes to your configuration templates, you can actually just do a redeploy of the packages. So in this particular case, let's say we have made changes to a template, issuing test and build on 5.3 would lead to a redeploy, whereas on 5.2 that doesn't have this feature, it would result in a package reload. So next up, we have the anatomy of one of these skeletons, or what one of these standard form Git repositories would look like. So I marked here out in the goldish yellowish tint. That's the files that are part of the standard skeleton, and in blue turquoise tint is the files that are sort of yours, right? If you wonder why I'm looking on the side here, it's because I have my second monitor. So going through things here, right? The most important things from the skeleton perspective. Or sorry, first the packages. So the packages directory is part of the skeleton, but the content of it is obviously yours, right? That's where you actually place your NSO package. So in the case of BG worker, this is where the actual NSO package BG worker lives. Second, we have the makefile. I've marked that blue here, like it's yours. It actually comes with the skeleton, but you're supposed to customize it. So that's why it's really yours. The makefile in turn includes NID common and NID package, which are two makefiles. These are the ones that define all those standard targets that we looked at, that starts a test environment, that defines the build, and also that figure out, whether to use the CI pipeline ID or to use your username to get unique names, things like that, right? Finally, the last part I want to show here is test packages. Again, this is part of the skeleton, whereas the content of it is yours, right? And packages in here, they're different from the packages directory because this is not considered part of the primary output of this repository. We place packages here that are used merely to do testing of our primary packages, right? So in this case, test BG worker, because it tests the BG worker package, right? It includes that as a library and then does, well, that logging that we just looked at. The packages on the other end are part of the primary output and will sort of be pushed further for use. Okay. Now you might wonder, I mean, if you have an NID package, how much work is it to get it working with NSO and Docker? Like the stuff that I showed you, if that takes days to set up, then maybe it's not worth it, right? But it doesn't. It's easy, and I'll show you just how quick and easy it is by doing it. So we're going to use the Nokia SROS CLI NED and place that in a Git repository using the NSO in Docker skeleton for NEDs. So let's switch to a terminal again. And here we go. So I've written down here in a file just the commands that we're going to run for this. So we're going to start here by copying the skeleton. This path is going to vary based on where you clone the NSO and Docker Git repository to. So I have it in here. Then you have the skeleton part, and we pick the NED skeleton. You copy that to a directory called ned alosrcli, so that will be our sort of project name here. Once we've done that, we're going to go into that directory. We initialize Git. We add all the files and commit. So at this point, we've just committed an empty skeleton, right? Then we extract the actual CLI NED, after which we add that to Git and commit it. At this point, we can now use these commands that we're by now familiar with, right? Make, build, and make, test, and start. So let's do just that. So here we go, and the Nokia SROS CLI NED, it's not the biggest NED, but it's still not trivially small. It has fairly good config coverage. So compiling it, which is what we're seeing now, actually takes a little while. Maybe I should have tacked on a time command to this do so we can just saw how quick all of this is. So, okay, building the NED is actually done, and now it's producing the various Docker images that's coming out of it, like the netsim container image, the test NSO. And now it's going in to actually start up the test environment. That again consists of pretty much the same thing that we saw earlier with the Cisco iOS CLI NED. Here's my mouse. Okay, so load, merge, add device. It does the exact same thing that we saw before, right? Adds the device, show device is brief, it fetches the host keys. This time around, you can see before we had the Cisco iOS NED, now it's the alosrcli NED. And if we want, we can go into director first. We can get the CLI here, show device is brief, and look at these things, right? Or if we want to continue dev1, we can do a sync from, right? And it will fetch the configuration, which again should be empty. Now, if we inspect the makefile, like I said, it comes with the skeleton, but you're supposed to make it, customize it. So it actually includes this test that I showed before, right? Configuring the host name, grepping for this magic string, right? Now, the one thing you need to do for using the NSO and Docker NED skeleton for a new NED is to modify, and it's marked here as well, right, with the to-do entry. So to complete the test from the NED skeleton, you have to provide the configuration to set the hostname on the device in the file that's called test device config hostname. So we can open that up. Just see, okay, here's another to-do entry marking this out. this assumes that you're going to set the host name using the IETF system model, which this device doesn't support. So we'll have to replace this with however you set the host name on a SROS device. Okay, and that was it. So that's how easy it is. Okay, coming back here. So what did we just build, right? I mean, we have our source code and we compile that into an NSO package. Now, in order to run and test that, we actually need NSO, right? So what we do is we have this NSO Docker image, base image, and we place our package on top of that, which then results in a Docker image that includes both NSO as well as our package and is ready to run. So I want to show you a few things around the NSO base image that we've used here that comes with the NSO and Docker repository, right? So complete NSO system consists of quite a few number of components. We have some going from the bottom here, right? So on the left side, we have some operating system. We have NSO itself. You have the Java and Python virtual machines. You have NEDs. You have service packages and maybe some Java and Python libraries in order to support your service packages, right? And with Docker, all of this is neatly arranged into layers that you see on the right. Now, the choice of NEDs and service packages is really up to you. Most services are specific to each installation, and there are hundreds of NEDs. And if you consider all the versions, there are probably millions of combinations. So which ones you pick is really up to you. Now, the bottom two layers, the Cisco NSO base, this is the common stuff and the thing that's coming out of this repository. It's called Cisco NSO base. So it's based on Debian Buster, and it includes NSO itself, Python and Java virtual machines, so you don't have to think about any of that stuff. So this image is based on an NSO system install, but it's then modified to make it more suitable for Docker. So running things in Docker is really different from running in a classic Unix environment. So I'd say the file system layout that we have in here is pretty thought through. It makes it easy to attach shared volumes for persistent data and logs. We keep things like packages in the Docker image, while other persistent data like CDB can be placed on this volume, right? And just as an example here, I mean, if you want to write your own, there are some pitfalls. It took me a little over a year to realize after building the first Docker image for NSO that NCS backup wasn't following symlinks, and so as I had the CDB directory pointed out by a symbolic link, I didn't have working backups for a year. Stuff like this is working in NSO and Docker. In fact, there's a test for this, a CI test that makes sure that NCS backup and restore is working. So it's sort of proven, and it's based on years of experience of doing this. Now the configuration for NSO is generated at startup, as is customary, I think, with Docker images. So you can influence it though through environment variables. The image helps you handle some stuff around SSH keys, TLS certificates, in particular when you're doing test and development, sort of you want to create temporary certificates. You also get some help with CDB compaction for NSO 4 to 5 upgrades. There's health check and various other things that overall just make this a pretty decent Docker image. Now, in addition to the Cisco NSO base, which is somewhat slim, it weighs in around ½ gig, there's also the Cisco NSO dev image, which comes loaded with compilers and all the tools that you need to build NSO packages. And that's, I think, ½ gig or something like that in size. The behavior of the Cisco NSO base image is tested in CI. So here's a screenshot from the public repository of NSO Docker. The middle column is sort of cut off here. It's much longer, actually, where we test these going between multiple versions of NSO. So it's like upgrade testing, right? And as you can see, I mean, we tested a fair number of NSO releases that it works correctly with the Docker, all the Docker stuff. And this screenshot is actually a little old. It tests more versions now that there are more versions. Now, in order to understand this just a little bit more in depth, I've included here the Docker file from the package skeleton. And this is the entirety of it, it's all. And it's pretty airy, if you ask me. So this is what is known as a multi-stage Docker file. And I'd like to go through it. So in the first stage here, we use the Cisco NSO dev image to compile our packages. Note that the version of NSO being a variable here, so that's part of what makes it easy to switch, like we've seen before. This stage is called build, which will be referred to later. And in here, we first copy in the source from outside the container into the build container. After that, we loop over our packages. We build them, compile them, and we optionally insert a build metadata file if one doesn't already exist. And if you haven't seen this in NSO, you can do show packages, right? And there's some build info stuff there. So this is going to update and set like the git sha, commit, checksum, build time, and things like that. So it's pretty nice. Then we enter the second stage, where we now start from the Cisco NSO base image. So using this multistage Docker file is what makes it possible to compile inside of a Docker container without polluting our source directory, and also make it a slim container, because we compile in one and we produce another one, right? So the target of this one, just like before, we had the NSO version, right? But the name of this stage is test NSO, and as the name indicates, this Docker image is just used for testing. We never use this in production. What we do here is we copy in, so from the build stage now, we copy in both packages and the test packages directory. And we also copy in this extra files from outside of the container into the container. So that's where you can place extra files that you want included in the container. And last here, in the third stage, now we start off from the special image called Scratch, which is literally empty, like Scratch, right? We name the output package, and again, we copy in our build packages from the build stage. But note here, we don't copy the test packages, just the package directory. Now in this container, since we're copying in just the packages and starting from scratch, there's nothing in here except for the packages. So there's nothing runnable. What we do is it just produces Docker image that can be used as a vessel that allows us to ship around our compiled package and use it somewhere else. We're using the Docker infrastructure to ship it around. You can think of it really as a tarball, right? Also notice how in here in this file, it doesn't say the name of an NSO package because it is 100% generic. We already saw how easy it was to use the skeleton, how little customization is needed, and that is largely due to its generic nature. You don't have to specify the name of your NSO package anywhere, just drop it in the packages directory. Now also, if you don't want to use these skeletons, you can start out with the Cisco NSO base image that I just showed and build from there. And that way you can still leverage on its functionality while being able to customize how you place and run things on top. Long term, I don't think this is necessarily a good idea. I think the skeletons really are quite useful. But on a short-term basis, maybe you're migrating from some other structure, and that could be really useful to do something more custom for your setup. So I try to visualize here what you get from the different skeletons. So the package skeleton we have here on the top, it outputs the package itself, this one, as well as the test NSO container image. We use the test NSO in testing to make sure that the package is okay. And once that's sort of complete, we can actually push the package one as a result. So this is the primary output. And by pushing it, I mean, in the CI pipeline, once we've seen the test pass successfully, we can push this to a Docker registry so that it's available for use by other repositories. Similarly, for the net skeleton, we have the test NSO container image, we have the package, they're used just in the same way, but we also have the netsim container image, which we use in testing, and we also see this as a primary output. So this is pushed forward and can be used by other repositories that want to have a netsim for testing, right? So finally, for the system skeleton, which we haven't looked at much, it only has a single NSO image that's used both for testing, but also considered sort of the primary output. So this doesn't contain any test packages, or it shouldn't. You'd have to test it sort of from its northbound interfaces. And this is something that we ultimately can deploy to production. There will likely also be an LSA skeleton in the near-term future. Now, being able to include other packages is really the basis of composition. So the skeleton offers a simple way to achieve this. Simply create a file. So I mean, imagine this is from another repository where we want to include the BG worker library, right? We want to have one of these background workers. So we include a library that helps us set that up. So in order to include it, we in the includes directory, create a file named bgworker, and this would be the content of it. We want to include bgworker/package. That's the actual name of the Docker image, and we tack on the NSO version at the end to keep the NSO version a parameter, right? Together with the dockerfile.in, that's part of the skeleton. The build process will then produce the actual Dockerfile, which looks like this. So this is what it then does. From this Docker image, we name that bgworker. Then later on, we copy in. I mean, notice this is just like how we copied in from the build stage. This time, we're going to copy in from what is the bgworker stage, right? So we just copy the packages from that. And that's how we've used these Docker images as sort of a shipping vessel. Okay, so why compose, right? I mean, the idea here is that we build these many small things and composing them together into a larger whole. And the reason for why you want to do this is that pretty much everything is easier when working on a small thing. So doing development, testing, running it, understanding it, all of this is typically simpler when you have a smaller thing, right? And with a more practical example, I've written down here on the right side, if you have NEDs, right? So NEDs, they tend to move slowly. You upgrade maybe once a month or maybe a couple of months in between, and they take a fairly long amount of time to compile. At least the XR and Juno's native netconf NEDs, because they weigh in at hundreds of thousands of lines of Yang models, so they take 5 minutes or more to compile. In contrast, your service packages, they move very fast, right? You typically commit to them every day. And when you compile them, even if it's thousands of lines of configuration templates, etc., right, it's typically quite fast and compiles in less than a minute. So by splitting these things up into different repositories, we can avoid recompiling the things that have not changed. The NEDs remain the same, so we don't have to recompile them every day. Compile them once, we get that binary output artifact, and then we just include that, which is a lot faster than just compiling them over and over again. As I've shown, a standard formatting repository exposes this standardized interface through all these make targets. Now we leverage this by wrapping a thin layer of GitLab CI configuration around it, allowing the whole thing to run in CI with no additional work. And by pushing your code to a GitLab instance, you can have it tested in GitLab CI, just as you saw the tests run locally. And conversely, having the ability to easily run the CI tests locally provides for a great developer experience. I mean, anyone, if you've set up CI before, you know how it typically goes. You know, you write some CI configuration, it doesn't work. So you change like a single character, you push that, you wait for the CI runner to pick it up, run the job, it's another failure, you go back changing very small things, and 76 commits later, you actually have something that's working, right? Here, all of that is sort of taken care for you already. So if you see problems in CI, you can easily reproduce that locally by just starting up this test environment locally, right? And again, we want to really encourage to run tests against multiple versions of NSO in parallel in CI, because that makes you ready to upgrade NSO. Okay, so I want to do a quick plug here for something called VRNet Lab. As I've shown with the NSO and Docker skeletons, the ones for NEDs, you get NetSim for free. NetSim is good for simple use cases. But the one main problem with it is that you don't get any real operational state. You would have to mock it. So if you configure something like a BGP neighbor, that doesn't mean there's actually going to be a BGP neighbor. So if you do show BGP neighbor, blah, 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 something, you won't get any output, right? This is because there's no BGP daemon running in NetSim. And once you start doing more self-tests and you want to monitor things, pre-post checks of software upgrades or whatever, then you want operational state. So to get closer to a real device, you want to use a virtual router. And VRNet Lab allows you to run these virtual machines or for virtual routers inside of a Docker container. And VRNet Lab sort of plugs right into the NSO and Docker environment. So it's really easy to replace a NetSim or even run both a NetSim and a virtual router. There are more advanced systems like Cisco CML or whatever, but I think this is a good step up. Although I guess I'm also not objective in this, since I originally wrote VRNet Lab. Okay, so I want to talk another sort of cool aspect of this. So NSO in Docker on Linux on Mac. When you consider most production NSOs, I think they run on Linux. And NSO in Docker runs on Linux. So both outside and inside the container, it's a Linux environment, right? So when you compile it, it's the same. Now, the interesting is that Docker on Mac OS X actually runs Linux as well. So technically under the hood, it's using the Xhype hypervisor on OS X to run a Linux VM. So when you interact on a Mac with Docker, that actually goes into this Linux VM and interacts with the Docker engine running on that Linux VM. Now, this is nice from the perspective that when we compile things, it's going to be exactly the same for our production system, for our Linux laptop, as well as our Mac laptop. If we use NSO and Docker, it's going to work the same across everything and have that same uniform feeling. Pretty cool. And with that, I'd like to wrap up. So thank you very much for listening. I've included here, this is the link to the main NSO and Docker repository. It's on NSO Developer Space on GitLab.com. So it's on GitHub. There's sort of a mirror between these two. I included the link to BG Worker. It's an open source package that you can use if you want to do the same thing. And since it's based on the NSO and Docker skeletons, you can sort of get a feel for how things work. There are also more repositories on the NSO Developer Space that, and some of which use the NSO and Docker sort of framework. I include my Twitter handle as well as my email address. So if you have any questions that you don't come up with right now, feel free to reach out to me. Right? Okay.
So thank you.
Yep.
Thank you, Kristian. Maybe I can ask you two quick questions before we close. One is actually people were asking the difference between the GitLab and the GitHub repository. And the second question was, when you have these different containers, how do you know how to connect to the device? Which, what are the device credentials in terms of, IP address and port when they're running in different containers, correct?
Right. So let's start with the first question there. So GitLab versus GitHub. I mean, this is really what we're trying to do there is just to make it sort of on the reader's terms. So a lot of people have a GitHub account, others have a GitLab account, and we really just want to make the code available on both. So if you look at NSO Docker, for example, the authoritative repository is on GitLab, because on GitLab we also have CI functionality. So if you want to open issues, for example, you should open issues on the GitLab version of it, but it is continuously mirrored. So any commits to the master branch are mirrored to the GitHub repository. So if you just want to get the code, you can get them from either one, and that's just fine. So that is really the sort of strategy moving forward here for all repositories. That's not the case yet, but that's the general direction that we want to move in. So that's the first thing on GitHub versus GitLab. The second part, I think what's being asked here is, how do we keep things apart, right? And this is really how it works. So for each of these test environments, you get your own Docker network. And that's just what I've shown here. So you can see, well, there's quite a few of them now. Where's my, yeah, so BG Worker, right? That was this one. We have the Cisco iOS CLI. There's this one with 5.2.1. There's another one for 5.3. And you can see my older ones here for other things, other projects as well, right? Now, having different networks simply means there's a different IP space within each of one of them, and host names that Docker resolves for us are just resolved within each Docker network. So if we look at the containers, now I have all the containers running here in parallel, and if we inspect one of them, so if I take this one, or Docker inspect test and, oops, what's it called? Cisco iOS CLI 604.5.3. I can see here it's connected to this network, right? So that is what keeps these different networks apart, and what enables that you can use this dev1 name in multiple different test environments at the same time. They really are not connected to each other. So that's pretty nice. I hope that answers the question. If not, then reach out to me.
Okay, we're about to leave, but maybe last point. What about Windows? Can I run all of this in a Windows environment?
Good question. I have not, right? I mean, I'm actually presenting this from a Windows laptop, and I mean, the terminal here is Windows, the Windows subsystem for Linux, so WSL, which is running Debian. But I've used SSH to reach another machine that I have. It's an Intel NUC here that sits on my desktop. That's a real Linux machine. Now, I tried to run Docker at some point, but it didn't really work properly. And I think this is because in WSL1, which is what I'm using here, the Linux interface, the POSIX interface, is emulated by the Windows kernel. There's a WSL2, which actually runs a Linux VM. So I imagine that Docker would run just fine on that. There is also Docker on Windows, which I have never tried. So I don't know, but I guess it could work. So that would be very interesting, actually, to look into. An area for future work.
I can add that Marco Sagosen lets us know that it works perfectly with the Windows subsystem for Linux. So
there you go.
Yeah.
Okay. We should add that somewhere on the README. So there's lots of information in the repository. It's not very super structured and easy to read maybe, but there's quite a bit of information there. Okay. Do we have any more questions? Do we have time for more questions?
No, we need to wrap up and close the session. So thank you.
Thank you.
Thanks
Thank you all
everyone.
for listening. Thank you.